We've seen AI make these incredible strides, right? Understanding language, generating amazing images,
Yeah.
even composing music.
Yeah, it's been pretty stunning progress.
But the real leap, the one that I think really fires up the imagination, is AI that can construct entire virtual worlds.
Mm-hmm.
Building diverse interactive environments for everything from like next-gen games to advanced training simulations, maybe even embodied AI for robots.
And what's fascinating, I think, is how quickly related technologies are sort of converging.
Right.
We've seen phenomenal progress in generating individual video clips, crafting these really intricate 3D scenes, even animating them over time in 4D.
It feels like we have this amazing toolkit building up.
Exactly. We have all these amazing tools, but the crucial challenge now is figuring out how to, well, orchestrate them. How do we put them together to create truly comprehensive and controllable virtual worlds?
Absolutely. And I think for anyone trying to keep track, it can feel a bit overwhelming. How do you even distinguish between all these impressive new models? How do you know which ones are genuinely capable of generating these interconnected virtual environments?
And maybe more importantly, how do we measure that progress?
Yeah. How do we even evaluate them?
That hits on a really fundamental question. I mean, right now, most of our benchmarks, they tend to focus on the quality of short single video segments. You mentioned VBench earlier. That's a prime example.
Okay.
And while those are valuable for, what they do, they don't really tell us if a model can generate a coherent sequence of scenes that fit together logically.
Or if we can actually control the layout, right?
Yeah.
Tell it where things should be.
Precisely. That explicit spatial control and the multi-scene generation aspect, they're largely missing from existing benchmarks. So it
Yeah.
sounds like the current tools just weren't really designed for this new frontier of world generation.
Exactly. Like, just because an AI can make a cool 10-second clip of a dog chasing a ball, that doesn't mean it can build the whole park, right? With trees and benches and other dogs all behaving consistently.
And then you have the issue that many of the really advanced 3D and 4D scene generation methods, they have their own specific input needs.
Ah, right, like camera specs or reference images.
Exactly, which makes it really hard to compare them fairly using those older video benchmarks. They're kind of apples and oranges.
So we need something unified.
We need a unified approach, yeah. Something that can evaluate all these different methods, 3D, 4D, text to video, image to video, using a consistent set of criteria that actually matters for world generation.
And that, I assume, brings us to the core of our deep dive today.
It does. It brings us to WorldScore.
Okay, so let's unpack this. WorldScore, developed by researchers at Stanford University, and it's specifically designed to evaluate these world generation models.
That's the one.
So our mission today, for you listening, is to understand what WorldScore is, how it actually works, and maybe most importantly, what it's telling us about where AI is right now in terms of building virtual worlds.
Okay, so the central idea behind WorldScore is, I think, quite clever. Instead of trying to evaluate the whole huge, complex process of world generation all at once.
Which sounds impossible.
Right. It breaks it down. It decomposes it into a sequence of smaller, more manageable steps. Think of it as evaluating a model's ability to do a series of next scene generation tasks.
Okay, so like building a world piece by piece. You start with scene 1, then the AI generates scene 2, then scene 3, and it all has to kind of hang together.
Exactly. And for each of these steps, WorldScore uses what they call a world specification.
A world specification.
Okay. It's basically a package of information that guides the model in creating that next scene. It includes a description of the current scene.
How? Like an image, text.
Both. An image and a text prompt for the current scene. Then there's a text prompt describing what the next scene should be like, and, crucially, the desired spatial layout.
Ah, the layout. That sounds key for control. What does that involve? Is it just like put a tree on the left?
It's a bit more specific than that. The layout spec has two main parts. First, there's a camera trajectory.
Okay.
Think of it as a sequence of virtual camera movements, panning, zooming, orbiting, that sort of thing. And this is described using precise camel matrices.
Whoa, okay. So like actual coordinates and angles telling the virtual camera exactly where to be and point.
Exactly. Very technical instructions. But then second, there's also a text description of that intended movement, something more intuitive like the camera smoothly zooms out.
I see. So you get both the technical detail and a human readable description. That probably helps different kinds of models understand the request.
That's the idea. And what's really innovative here is that WorldScore can evaluate this incredibly diverse range of models. Doesn't matter if it's making static 3D scenes, dynamic 4D scenes, text to video, image to video.
How does it compare them if they're so different?
Because the crucial thing is, they all ultimately produce their output in a common format, a rendered or generated video.
Ah, okay. Standardization.
Exactly. That standardization allows for direct, meaningful comparisons across these fundamentally different techniques. So we know how it frames the task, but what are they actually testing these models on? Let's talk about the WorldScore dataset.
Right. You need good test cases. So
Yeah.
tell us about the data set. How big is it? What kinds of worlds does it cover?
It's pretty substantial, 3,000 test examples. And the key thing is its breadth and diversity. It includes both static worlds,
Like rooms or landscapes?
exactly, various types of indoor spaces, outdoor landscapes, and also dynamic worlds that feature different kinds of motion and change. Plus, it covers both photorealistic scenes and a range of stylized visuals like anime or cyberpunk.
Wow. Okay. That's a really wide net.
Yeah.
Could you give us a few more specifics? Like what kinds of static and dynamic worlds are we talking about?
Sure. For static worlds, they broke it down into 10 types. 5 indoor, dining, living rooms, passageways, public spaces like museums and workspaces,
Go ahead.
and 5 outdoor, cityscapes, suburbs, aquatic landscapes, terrestrial ones like deserts or forests, and verdant, grassy landscapes.
Got it. And the dynamic ones.
For dynamic worlds, they identified 5 distinct types of motion. Things like articulated motion, think a robot arm moving, deformable motion like cloth rippling,
Mm-hmm.
fluid motion water, smoke, rigid body motion like a bouncing ball, and then multi-motion scenes where several of these things are happening at once.
That level of detail must make the evaluation really informative. How did they actually create all these examples, especially the realistic ones?
Yeah, the curation process for the photorealistic starting images was incredibly rigorous. They pulled images from open source datasets, also used Unsplash.
Right.
But then these images went through multiple filtering stages, checking for visual quality, making sure the camera perspective was reasonable, checking for similarity within categories, consistent lighting.
Sounds intensive.
It was. They even used AI tools like CLIP IQA and CLIP Aesthetic for quality checks and perspective fields to analyze the viewpoint. And then after all that, human reviewers gave a final look to catch anything the automated systems missed.
Wow. Okay. Very thorough. What about the stylized scenes then? How did they generate those? Anime cyberpunk, you said.
Yeah, so for each photorealistic scene, they randomly picked one of 7 styles. Anime, cyberpunk, Chinese ink painting, ukiyo-e, impressionism, post-impressionism, even Minecraft style.
Minecraft. Okay.
Yep. And then they used a style-controlled text-to-image model. They basically gave the original scene description plus an instruction for the specific style, and it generated the stylized version.
That's a neat way to get variety from the same base content. Now, how did they define the next scene? What's supposed to happen in the sequence?
Ah, right. This is where they brought in the large language models. They used an auto-regressive process with an LLM. They mentioned GPT-4 specifically.
Okay.
So the LLM generated a text description for the next scene, aiming for something that was coherent with the current scene, but also introduced something new or changed.
And they made longer sequences too, right?
Yeah, they created both small worlds, just one new scene, and large worlds with 3 new scenes. That was specifically to test how well models maintain coherence and control over longer stretches.
Makes sense. And the camera movements, the layouts, how were those set up?
They curated a set of 8 common camera movements, the kind you see in filmmaking. Push in, pull out, orbit right, orbit left, move sideways, pan right, pan left.
Standard cinematic moves.
Pretty much.
Right.
And for each step in generating a static world sequence, one of these layouts was randomly assigned. And interestingly, if the layout was something within the current scene, like a pan or an orbit,
Yeah.
sometimes they deliberately kept the text prompt for the next scene the same as the current one
Why do that?
to isolate the camera control. It let them specifically evaluate if the model could execute the camera movement accurately without the extra challenge of also generating totally new content at the same time.
Ah, clever. Okay, so we've got this detailed, diverse data set. The task is generate the next scene based on the current scene, a text prompt, and a camera layout.
Okay.
Now, the big question, how does WorldScore measure how well the models do? What are the actual metrics?
Right, the evaluation. WorldScore looks at 3 main things. Controllability, did it follow instructions? Quality, does it look good and consistent? And
Right.
dynamics, how well does it handle motion?
Okay, 3 pillars.
Exactly. And under each of those, there's a set of specific quantitative metrics.
Let's start with controllability. How do they measure if the model actually listened to the instructions about the camera, the objects, the scene?
Okay, three main metrics here. First, camera controllability. This measures how accurately the generated video matches the instructed camera path. They use a pretty sophisticated algorithm called Droid Slam. It estimates the actual camera movement in the generated video. Then they compare that estimated path to the intended ground truth path.
And that gives you error scores.
Yeah, quantitative errors for rotation and translation of the camera tells you how far off it was.
Okay, so if you said pan left smoothly, this checks if it actually did that and how accurately. What's next for controllability?
Second is object controllability. This checks if the specific objects mentioned in the text prompt for the next scene actually show up in the video.
Makes sense. How do they check that automatically?
They use a state-of-the-art open set object detector. It scans the generated frames, identifies objects, and checks if they match what the prompt asked for.
So if you ask for a cat, does it find a cat? Simple enough. And the third part of controllability.
That's content alignment. So while object control looks at specific items, this takes a broader view. It assesses the overall semantic match between the generated scenes and the entire text description for the next scene.
How do they measure that kind of overall match?
They use CLIP score. It's a well-known metric for measuring how well an image or video semantically aligns with a piece of text. Higher score means better alignment.
Okay, so that covers how well the AI follows orders. Now, what about the quality of the world itself? How is that evaluated?
Right, quality. 4 key metrics here. First is 3D consistency. This looks at the stability of the scene's geometry across the video frames.
So does the world feel solid and stable?
Exactly. They use Droid Slam again for this. It estimates depth, and the metric measures something called reprojection error between frames. High error means the 3D structure looks wobbly or inconsistent.
Crucial for immersion. You don't want walls pulsing or objects warping. What's the second quality metric?
That's photometric consistency. So 3D consistency is about geometry. This is about appearance, the textures, the colors.
Okay.
A common problem in video generation is texture flickering, right? Things shimmering unrealistically. This metric uses optical flow tracking pixel movement between frames and calculates the average endpoint error, or AEPE. It's good at catching those subtle appearance shifts.
So a mountain should stay looking like the same mountain texture-wise, frame to frame.
Got it.
Third quality metric.
Style consistency.
Yeah.
This is mainly for the stylized world. It checks if the visual style, like anime or impressionism, stays consistent from the beginning to the end of the sequence.
And how do they measure style?
They compare something called gram matrices between the first and last frames. You can think of these matrices as capturing the stylistic fingerprint of an image.
Interesting. And the last quality metric.
Subjective quality. Because ultimately, we want worlds that look good to us, to humans.
Right. But you can't ask humans to rate thousands of videos.
Exactly. So they did a preliminary human study with 200 participants rating videos. Based on that, they chose an ensemble of automatic metrics, CLIP IQA+, and CLIP aesthetic, that correlated best with human judgments. So it's an automated proxy for human perceptual quality.
Trying to get the machine to judge quality like a human would. Okay, interesting approach. That covers quality. What about the final pillar? Dynamics. How does WorldScore measure motion?
3 metrics for dynamics. First, motion accuracy. This checks if the motion specified in the text prompt actually happens in the right place in the video.
So if it says car drives past,
Yeah.
does the car move, but maybe the buildings don't?
Precisely. They use annotated motion masks, basically outlining the areas where motion should happen, using a tool called SAM2, and compared the optical flow inside those masks versus outside.
Okay, ensuring the right things move. What else?
Second is motion magnitude. Pretty straightforward. How much motion is there? It's just the median optical flow magnitude across the video, helps gauge if the model can create significant movement when asked.
And the last dynamics metric.
Motion smoothness. You know how generated video can sometimes look jerky or jittery?
Yeah, that temporal inconsistency.
Right. To evaluate smoothness, they use a standard video frame interpolation model. The idea is if the original motion is smooth, the interpolation model should be able to predict the in-between frames accurately. They compare the generated frames to these interpolated frames to quantify the jitter.
Okay, that's a really comprehensive suite of metrics, covering control, quality, dynamics. So what happened when they actually ran these tests? They evaluated quite a few models, right?
They did.
Wow.
19 different models covering the main approaches: image to video, text to video, 3D scene generation, even a 4D model.
And what were the big takeaways? Any surprises?
Well, one clear finding was that the 3D scene generation models like Wonderworld and Lucid Dreamer, they generally nailed the static world generation.
How so?
They showed really high camera controllability, good content alignment with the prompts, and excellent 3D and photometric consistency. Solid, stable scenes,
But there's always but.
but they don't generate dynamic worlds, they build static scenes. And interestingly, the 140 model they tested, 4DFi, didn't perform quite as well as maybe expected. It suggests that getting controllable, consistent dynamic scenes is still a really tough nut to crack.
That makes sense. Building a static world is one challenge. Making it move realistically and controllably is another level. What about the video models then?
The video models, both text to video and image to video, showed a pretty significant weakness across the board in camera controllability.
Really? Even the best ones?
Even the best video model for camera control was still way below the 3D and 4D approaches. This looks like a major bottleneck for video models trying to achieve good static world generation. They seem to struggle with precisely controlling the viewpoint and layout.
So telling a video model pan left 30 degrees is just hard for them right now. Why do you think that is?
That's a great question. It probably has to do with how they're trained. They often learn associations between text or images and plausible visual changes, rather than learning an explicit mapping between, say, camera parameters and pixel output.
So they're guessing the movement rather than calculating it.
Kind of. It might need new architectures or training data that explicitly teaches that camera to pixels relationship.
Interesting. What else stood out from the model comparisons?
Well, something cool is that the best open source image to video model they tested, CogVideo Xi2V, actually performed surprisingly well. It held its own, sometimes even matching or beating leading closed source models like Gen 3 and Hailu on both the static and dynamic tasks overall.
Wow. But I sense another but coming.
Well, yeah, it wasn't universally better. For instance, CogVideo Xi2V might have had better camera control than some closed models, but it lagged behind in object control and content alignment. It really shows that different models have different strengths and weaknesses. There's no single winner yet.
So lots of trade-offs. Did any other interesting trade-offs pop up?
Definitely. In video models, there was a clear trade-off between motion magnitude and motion smoothness.
Ah, so models making big movements were often jerkier.
Exactly. More dramatic motion often came with less smoothness, more jitter. And another thing, bigger motion didn't necessarily mean more accurate motion.
Meeting.
Just because a model could make things move a lot didn't mean the movement happened in the right place or followed the prompt accurately. There wasn't a strong link between motion size and motion accuracy.
That's important. Big movement isn't useful if it's the wrong movement. Any other limitations uncovered?
A couple more things. Video models generally struggled more with the large worlds, generating longer, coherent sequences. They also tended to do worse on outdoor scenes compared to indoor ones.
Any idea why outdoors might be harder? More
Yeah.
complexity?
Potentially.
Yeah.
More variation, less constrained geometry, maybe. And one final point. Text-to-video models generally seemed easier to steer.
Easier than image to video.
Yeah, they tended to show better controllability overall and could generate larger motion. The image-to-video models often seemed kind of stuck to the viewpoint of the starting image. It highlighted a real challenge in getting I2V models to generate truly new scene content that moves away from that initial view.
Okay, let's try and summarize these findings then. WorldScore is giving us this much-needed, standardized, very detailed way to look at AI world generation, which is moving incredibly fast.
Right. It's a crucial tool right now.
And it's highlighting where different approaches are strong, like 3D models for static, controllable scenes, but also where the big gaps are.
Exactly. Integrating controllable dynamics into those stable worlds is a huge hurdle. And for the video models, getting that precise camera control, handling longer sequences, diverse environments, those are major challenges.
It really feels like WorldScore could help guide the research now.
I think so. By breaking it down into these specific metrics, researchers can target their efforts. Like, okay, we need to really focus on camera control for video models, or how do we add robust dynamics to our 3D generator? It gives clear benchmarks to aim for.
Absolutely. So as a final thought for you, our listener, as you think about these findings, consider what the future of these immersive, interactive virtual worlds might look like. What aspects of world generation do you think are most critical? Is it the pinpoint control, the visual realism, the believable physics and dynamics, maybe something else.
Yeah, what matters most for the applications you can imagine, whether it's gaming, education, simulation, or robotics, is worth thinking about. And definitely, if you're interested, check out the WorldScore website. The link's in our abstract. You can see the benchmark, the data, the detailed results. It's a really fascinating look at how we're starting to teach AI to build realities from scratch.